So anyway, most of my classes were online and it worked well for some people. But to be perfectly honest, for a lot of people in my classes, they just had a really hard time managing, staying on task, watching the videos, as they came out, coming and asking questions, et cetera, and so on. And so that's why I'm doing this live thing on Monday, Wednesday, trying to come in person once a week. It's not for me. I would much, much rather be at home. I want to be perfectly honest with you. I'd rather be sitting in my office. I would feel safer. I have where this thing keeps going actually, but let me just open the picture back up. I've got a 1-month-old son at home, a newborn at home. I'm perfectly honest with you, very scared about bringing the virus home. Okay, he's a newborn. Who knows how well his immune system can handle something like that. I would much, much, much rather be at home. I'm trying to do this because I would like to see more people be successful in my class this semester compared to last semester. And this is a harder class than the class I taught last semester. So that's just the facts, okay? And so I have a zero tolerance policy about masks and stuff. It's great to see everyone with it. If people start messing around, I'm just gonna probably ask you to leave. I'm not gonna give you a warning or anything. Just do your best to respect me and my 1-month-old son, and we'll be fine, I think. Okay? Thanks. I just wanted to sort of be upfront about that. I'm really not gonna tolerate anything that messes around with that. Are there questions about the quiz at all or what you should be doing tonight? Can I clarify anything at all? Because I'm going to jump into some notes in a second. I'm going to use my iPad. And can I clarify anything for anyone before we do that? Remind myself exactly what I'm going to do. I'm doing this. And I'm going to do this. And I'm going to do this. I'm just doing this to record the session so that I can post it with the other stuff online. I don't anticipate anyone will be with us remotely today, but occasionally that might potentially happen. I'll just ask you to slide over maybe 1 or 2 seats or just make me a little bit uncomfortable being that close. Thank you. All right. And my goal kind of moving forward is to do this even with the remote sessions, using my iPad. And that way it'll be a running complete list of everything that complete notes of everything we cover. And my plan is to share with you like a Google link so you can just access these notes remotely whenever you want. So that's the other nice thing I think potentially about using an iPad moving forward. The downside is we filled out these notes last class and I don't have them on my iPad. So I'm just going to sort of quickly remind us what we have done so far. So we looked at the definition of a limit originally, which was this definition right here. And we looked at some examples of how to estimate these limits from the right and the left-hand side using like rudimentary, what I would refer to as not cheating, but like not really using math, right? Like we did it using a graph, right? Like we graphed some stuff and looked at pictures. And then right here was where we built a table. And so hopefully you have these notes and you can kind of reference them right now. Again, if you don't have these notes, you should definitely be printing these after class. You should have had them last class, I'd say. If you don't have them, go over to the library. And then this page was looking at some, examples where the left hand and or the right hand limit might not exist, right? So this first one here was showing it was like something like this, something like this. And so that was showing the right hand limit and the left hand limit exist, but are not equal. This one was showing vertical asymptote. This graph looked like this, I believe. And so if we tried to approach one, the left hand and the right hand limits shoot up to infinity, and so they didn't exist. We looked at the sine one, which kind of does this kind of thing. And as you get closer to 0, it starts to really oscillate like that. And so if we tried to approach 0 in that one, it wasn't going to work. And then ln does this thing. And so if we try to approach 0 from the left, there's no graph here, right? That's what we looked at last time. And so I'm just trying to remind you, like, we saw what a limit is. We kind of looked at some rudimentary ways of evaluating them or estimating them. And then we looked at some situations where they don't exist. Okay, so now we're getting into evaluating them by hand, not using a table, not using a graph, using some other more advanced method. Okay. Let me think here real quick. I think I'm actually going to switch over and do this. Give me 1 second. I'd like to have my notes up over here. Now let me pull my notes up. Okay. So, again, we use tables and graphs in the last couple of classes. We want to be able to do this stuff by hand without using a calculator or something. And so that's what we're moving into, right? We eventually want to be able to evaluate these kind of limits down at the bottom here just by hand. And so the way we're trying to think about that is by first starting with some basic properties. And so these basic properties just sort of tell us what to do if we have functions that are being added or subtracted or multiplied or divided inside a limit, right? That's what's going on in this thing on the right here. It's like there's some functions, they're either being added or subtracted, maybe they're being multiplied, right? Maybe they're being divided. How do we evaluate those limits? This is what it's telling us how to do. And so it's all based on this thing at the top here. So it's like we have two separate functions, f of x and g of x. Let's pretend that they themselves have limits that exist. If they themselves have limits that exist, and you want to evaluate the sum of their limits, like this one, for example, then you just take their individual limits, L and K, and you add them together, right? That's what this is telling us. And so I'm going to go into a little more detail here and show you some specific examples. But that's sort of the abstract way to think about what these properties are saying. So let's pick a couple of functions and work with those. So let's let f of x be x squared, and let's let g of x be x plus 1. Right, those are two very simple polynomial functions. And it turns out with polynomials, you can plug numbers right into those functions. So let's jump ahead actually to theorem 2. That's exactly what this says right here. It's telling us if we have polynomials and we want to take a limit, you just plug the number right in. What's a polynomial? Maybe we should start there. Does anyone remember what that means? I know we talked about that in my pre-calc class, but that's just like a vocab word. We should generally know what it means. Anyone know what a polynomial means? What's a function that's a polynomial? Or what would characterize a polynomial? Any thoughts about that? Polynomials. So these are functions that have non-negative whole-powered exponents. So the things I wrote at the top of the page are polynomials. Right, these are polynomials because the power here is a 2, the power here is a 1, the power here is a 0. So they're whole-powered, they're non-negative. So what this property is telling us here, so let me write down a couple other examples. So like x squared plus 1 is an example, pi x minus 6 is an example, 2x to the third plus 4x minus 8 is a polynomial, right? All these things have whole-powered exponents that are not negative, okay? And so what this thing right here is telling us then is that if you want to take the limit of a polynomial, right, so x is approaching c in that thing, you just plug c right into the thing. That's what that's saying, right? So for example, if we wanted to do the limit as x approaches, say, 3 of x squared plus 1, this theorem is just telling us you can just plug 3 right into that function. See that? Does everyone you know, and then, I don't know if I've said this yet. I definitely said it in my last class. One of the major, important, hard things about math, like most of the time, I'm literally think like probably more than half the time, is just understanding the notation. Like being able to look at a property like that and having some sense of what it means and how to apply it. Right? If you can do that, that's like half the battle, right? And I understand that it's a different language and it's sort of confusing to look at, but that's like one of the main things that we're trying to do here is like read something like that theorem and understand what it's telling us. So based on number one in my example, you kind of see what I'm saying there. We're trying to take a limit of a polynomial. You can just plug the number right in. That's what number one, that's what this thing's telling us right here. Is that okay? Thanks. Absolutely. So there's been 9 plus 1. Yeah. Thanks. Keep those. There's no dumb questions too. There's only dumb professors sometimes. Hey, let's give an attendance too. Do you mind just telling me your name? Who just came in? Thank you. Welcome. All right. Other thoughts about that property? Number one, how to read that, how to make sense of it. What's number two say then? Number two is very similar. So P and Q are polynomials. In number two, we're doing a limit, but there's a fraction. What's it say? So here's an example of this. Let's say we have the limit as x approaches 0 of x plus 1 over x squared minus 6. Right? Those are two polynomials. We're dividing them. We've got a limit as x goes to 0. What's that property say we can do? Do the same thing. Just plug the number right in. Right? We're approaching c over here, and right here we've plugged c in. Right? And so this just says we can plug those numbers right in and get 1/6 or minus 1/6. And so I wanted to start with theorem 2 here because we're going to go back up and use it in theorem 1. Questions about what theorem 2 is saying? So if we have a polynomial, limits are super, super easy. Just plug the number in. And it's been a couple of years, actually, it's been 3 or 4 years since I taught this class. But in the past, I often put questions like this on test. Right, this is like the easiest limit question possible. Just plug the number in. And it's either going to be the easiest question on the quiz or you're going to get it wrong because you're just like confused by it, right? So just trying to understand and remember what we're trying to do. We're trying to eventually plug the number in, right? And this is telling us if we have a polynomial, you should be able to plug the number right in. Okay. So back up to the property number one, or this theorem number one then. If we've got two polynomials at the top of the page, right? We've got two polynomials up here. These are two polynomials. If we did a limit with those things, you can just plug the number right in. So for example, let's do the limit as x approaches 2 of this thing. That's just going to be 3, no problem. And if we did it with x squared, you also just plug the number in. And so what I'm trying to do is I'm trying to set up this situation with an f of x and a g of x that looks like this right here, right? We now have two specific functions that have limits. In one case, L is 4, right? And in the other case, K is 3. Ooh, that was a bad color choice. You can ask a question, yeah. What is what is that? That's after the 3 or the 4. So it's saying like, let's look at it. And these are kind of silly examples because they're super easy functions. We're trying to start with easy functions before we move on to more complicated things that look like these ones, right? So I'm trying to illustrate ideas with easy functions. So the idea is x squared. We look at these graphically, so we can come back to graphically. If we're approaching 2, we're thinking about where is the function around 2. Since it's a polynomial, we can just plug the number right in and see that we get 4. Right? And so the idea is as we approach 2 from the left on this function or from the right, if both approaching the same number of 4. Again, this is a super easy one, so all we need to do is plug the number in. Eventually, we want to be able to look at functions that might look like this, or maybe there's a hole right there, and we want to know the limit as x goes to 0. We can't plug 0 in because there's a hole, and so we want to be able to figure out what is that point, right? Question mark. What is that point right there on that limit? And kind of extending further, we care about limits because we're going to use them to derive derivatives. So it's something, it's like a building block for the really important thing in the course. Does that answer your question a little bit? So if it's a polynomial, it's just the output, right? Input, output. But we care about things other than polynomials. Most of the things in the world are not polynomials, especially interesting functions. And so we're using this idea to build towards more complicated things. Other thoughts so far? So everyone sees that I have like this situation. Come on, man, let's go. This situation is all set up with those functions at the top there, right? So for example, let's look at property number 1 then. Property number 1 says, if we're going to take the limit of a constant, it just stays the same. So number 1, for example, would be like, the limit as x approaches 2 of the number 10 is just 10. If you have a constant function like 10, there's the function y equals 10. And if you want to approach the number 2, you're just walking along this graph and you're at 10 the whole time. Right? Nothing's changing there. And so that's what this property says. This property says if you just have a constant function, it doesn't matter what limit you look at, nothing's changing in that function. There's no x's, right? In the function y equals 10, there's no x's. There's nothing to plug numbers into, so it just stays the same. That's literally what property number 1 says. Whereas property number 2, right, this second one here, tells us what to do with the function y equals x. And now this one says, if you want to do the limit of y equals x, and you're approaching c, that just ends up being the answer. And that should make sense because it's a polynomial. You're just walking along that line near points, right? So an example number 2 would be like, if we want to approach 2 of x, this just ends up getting plugged in there because we know we can plug things into polynomials, and that just ends up being the answer. All right, I just rambled for a minute there. Can I answer some other questions? The limit exists, yeah. So the picture's getting cut off a little bit on the other. I don't know why it's doing that. Maybe if I do that. Because if we're walking along this graph on the left or the right, it's both approaching that middle point, right? And the fact is, because there's a constant function, it's not changing. It's not like you're at like 9, 9.9, and then you're getting closer to 10. You're just at 10 the whole time. So you're right at 10 the whole time. And so any limit you could ever want to look at is going to end up being 10. Where the second one, if we kind of drew the second one out, y equals x is a graph that looks like this. It's a line that's y equals x. And so if we care about where y equals x is at 2, that is changing. That's I don't have that up here. That's right here. And so it turns out that's going to be at 2. Right? If you walk along this line from the left, you're approaching 2. And if you walk along that line from the right, you're also going to be approaching 2. But the numbers do change in this one, right? They get negative, they go positive, so they're changing. The one on the top is just sticking right at 10. Other thoughts, questions about that? What those properties are saying? So then I'm not going to go through all of them, but I'll do a couple of the key ones here. The third one is saying what to do if we add 2 functions together. So remember, we have our functions at the top here, x squared and x plus 1. Number 3 is telling us what we could do if we wanted to do the limit of the two of them being added together. Right. I have a limit, x approaches 2. I have two separate functions being added. One of them is x squared, one of it is x plus 1. Well, those two things have individual limits at the top. And so what this property is saying is, if we want to evaluate the limit of two things being added, you just add or subtract their individual limits. Right? It's getting covered a little bit here, but that's what this is saying. Right? If you want to add or subtract functions inside a limit, just add or subtract their individual limits. So if we know these two things have limits themselves, we just look at them separately. Right? And we do know that one of them converges to 4, one of them goes to 3. So this is just going to end up being 4 plus 3, or 7. Right? And if we subtracted them, we would just subtract the two things. Thoughts? They're all kind of follow very similar to that, to these same kind of ideas. Right. Number 6 is what to do if you divide them. Number 5 is what to do if you multiply them. All right, let's look at, we kind of already looked at 6 in the polynomial one. Maybe we'll just look at 7 real quick. 7 says, like, what if I wanted to do the limit as x approaches 2 of x plus 1 raised to the 6th power or something, right? That's what number 7 tells us what to do if we would have a function raised to a power. Well, I know x plus 1 goes to 3, right? And so this is just saying take the individual limit and raise it to that power. And so this is going to end up being 3 to the 6th. Whatever that is, I don't have a calculator and I'm not interested in really, it doesn't really matter. Thoughts about how to apply those things, these properties. I'll come back to this in a second, but just looking ahead, it's kind of like when we look at something like this, then we've got two things being subtracted, and each one of those things is a fraction. And so those properties up top say we can look at their individual limits, and then we can go into the fraction and look at the top and the bottom separately as well. Right, so it gives us sort of a roadmap of how to approach limit problems. Oops, there we go. Can I clarify something about these properties? We're going to keep using them, and if it's not clear, I hope it becomes more clear, but can I clarify something currently about it? All right. Just the last property I'm just going to just very quickly touch on. It just tells us a very similar thing about trig functions, right? So it says, hey, if you can plug the letter C into one of these functions, so C is in the domain, right? In all of these properties, the limit is x approaches C. C is some number you can plug into the function, it's in the domain. What this is saying is if you want to do one of those limits, you just plug the number right into the function. Just like it's very similar to the one right above it. I'm just going to write that in words real quick. So what these things are telling us is you can just plug the value x is approaching directly into trig functions. We don't do a lot with trig functions in here. Oh, there's also some exponentials and logs in there as well. We'll do a little bit. The trig comes up more often than not in Calc 2, in my opinion. We'll see them. We'll look at them in a little bit. We'll look at the derivatives and things like that, but it gets a little more intense in Calc 2. All right, let's look at some examples. Keep going. Are there questions about what I'm trying to say on this page so far? All right, so let's look at this. This is our first example of like a trickier kind of limit, right? We're taking the limit as t goes to 0. It's a fraction, there's a square root in it, there's squares, so it's a little bit trickier. And notice what the properties tell us we can do, right? The property here tells us if we have things being divided, we look at their individual limits. And then if we have things being added or subtracted, we look at their individual limits as well. And so that lets us go inside the fraction and then moreover, go inside the numerator once we go inside the fraction. In other words, using the properties at top there, this becomes the limit as t goes to 0 of the numerator right? So that's property 6 right there. And then inside the numerator, we have things being subtracted. And property 3 tells us if we have things being subtracted, you can just subtract their individual limits. And so this number of property 3, so from here to here is going to be property 3, lets us go inside and do the limit on the numerator like this. Okay, see how we just applied some of those properties on the previous page where it tells us what to do with fractions, tells us what to do with adding and subtraction. And really what it boils down to is you kind of look at each individual piece. Okay. And moreover, one of those properties tells us what to do with this one too. What's the limit as t goes to 0 of 3? Which property is that up there? Yeah, it's a constant, right? So this is number 1. Right, the property number 1 says if you got a constant, it just stays the same. And so notice what happens as we start to evaluate each one of these things. So I'm going to plug, so this is an important thing too. Notice how I'm writing lots of limits on here. Started with a limit, I put it into the numerator and the denominator, it distributed into the numerator. I've got limits all throughout. You need to keep writing that until you actually plug the number in. Right, this is a mathematical argument. When I read this, I read it like a sentence. And without the limits being put in there where they're supposed to go, it's like a garbled sentence. It's like something that doesn't make sense. And so I'm going to plug the numbers in now. And so I'm going to stop writing the limit, right? So I'm going to plug in 0. So I'm not going to write limit anymore. Right, so I don't have limits anymore because I plugged it in. But notice what happens. We end up with 3 minus 3 over 0. We get 0 over 0. That's no good. That's what's called an indeterminate form. If you want to know how to spell it, it's right down below here. And so we're applying these properties. We want to do it by hand, but we're realizing, oh shoot, this didn't really work. And so we need a few techniques to handle these indeterminate forms. Let me just pause there and see if anyone's confused about that. What we're doing here so far. Anything? All right. So even when we want to do these things by hand, sometimes they're super easy, right? Like this one right here. It's a polynomial, you can just plug it right in. More often than not, they're going to be funky like this one. And so there's a bunch of different kinds of indeterminate forms. Here they are. Here they are. Right, we just saw one of them, 0 over 0. If you evaluate limits and you get infinity over infinity, like what are these things? Is that 1? You're dividing something by itself, kind of, but you're not supposed to divide by 0. That's weird. Is that 0? Is that 1? Is that undefined? Same thing with that. Also very strange, right? Infinity minus infinity. Is that infinity or 0? Something else. I don't know. Right. So all things that look kind of weird. These are all kind of weird looking, right? 0 times infinity. What does that mean? If you get one of these indeterminate forms, we need some other technique. And that's really what this chapter is a lot about, is like understanding limits and then understanding some of the techniques to solving them. And that's where this stuff comes in, these three ideas. So we're going to look at three ways to look at, oh, there's one we want to add too. So 0 over 0 is one type, but really anything over 0 is no good, right? If you have like any number over 0, you really need to rethink it if you get something over 0. Okay, we'll look at three techniques. Like it says right here. We'll either A, multiply something by 1 and do some algebra. B, we'll factor and cancel. That's a nice thing if it works. Right, that's the second thing. Or C, we'll combine terms. And so we're going to go through each one of these techniques, look at an example, kind of think about how we know which one to choose. And by the end of this, the next couple pages, you'll be able to do all the homework for next week. So we're just going to go through them one at a time. Let's start with multiplying by 1. So if you multiply something by 1, it doesn't change the problem, right? You have some function, you multiply by 1, it stays the same. And so that's kind of the underlying principle here, is when you multiply by 1, it doesn't change the problem. But what it lets you do is manipulate what you currently have to something that is easier to work with. And so the first thing we're going to look at is the conjugate over conjugate thing, right? Has anyone heard that word before? Conjugate? Anyone heard that? Makes me think of something specific. It always makes me think of Spanish, but that's not what we're talking about, right? We're not conjugating verbs in Spanish or something like that. Where the conjugate in math has to do with square roots. And so we use the conjugate method. Let's learn what conjugate means first. So the conjugate of this expression, square root of f of x plus or minus g of x, is the exact same thing, but you switch the sign between them. Okay? So the thing that changed here is that this turned into this. So if it was a plus between them, it becomes a minus. If it's a minus between them, it becomes a plus. That's the definition of a conjugate. And it's helpful in this case because when you multiply a function that has a square root by its conjugate, things cancel and you end up eliminating the square root. And so if you have a square root problem, it's very helpful to use that way. So that's what we're going to do on this particular function, on this first one here. We're going to multiply by the conjugate, and let's evaluate why we need to, right? You should always try to plug the number in, just like this one. Right? You always try to plug the number in. So on this particular one, this limit as t goes to 0, let's try to plug 0 in. Right, we just did this a second ago, I guess. I forgot we did this up there. This ends up being 0 over 0. So we need another technique. And what I'm suggesting is, if you've got a square root and you end up with indeterminate form, you should multiply by conjugate over conjugate. Okay, so what I'm trying to say based on these two things is, when a square root is causing indeterminate form, you should multiply by the conjugate. And not just the conjugate, but it needs to be the conjugate divided by itself. Otherwise, you're changing the problem, right? If you multiply by conjugate over conjugate, that just equals 1, right? That just equals the number 1. So you're taking a function, multiplying it by 1. You're not changing anything, but you'll see it's a nice technique to help move forward. You know, math is all about these weird little techniques. Just like knowing some little trick to move on to the next step, I swear. Especially when you get into really advanced math, you like run into dead ends, and then it's like, oh yeah, well, I know if I just multiply by the conjugate, like this cool thing happens. And how do you know that? It's just something that you learned along the way. So let's do it though. Let's start with our original thing. Let's multiply by the conjugate. This is the conjugate. the exact same thing, but you change the sign between the two values. Right, so notice how the plus is still between the inside the square root, right? We didn't change what's in the square root. We changed what was between the square root and not the square root. That's a really important thing to keep in mind. Does everyone see that? This plus is still a plus. It's the thing between the two that changed. With me on that? All right. So when we keep going, what's going to happen is things are going to cancel, and in a nice way. But we need to distribute. Right, we've got this thing in parentheses over here. It's multiplying something in a parenthesis. So we need to FOIL, right? Like 3 multiplies this, 3 multiplies that, square root multiplies this, square root multiplies that, right? We distribute everything out. And when we do that, we get the following. Right, we'll have a -3 plus 3, so those are going to cancel. And then a -9. And I'll write that as 3 times 3. And I'm not going to multiply the bottom out because it's going to actually help us to leave it factored like that. Let me pause here. I know that's some potentially tricky algebra going on, so let me know if that looks okay. Oops. Is everyone okay with that distribution? All right, everything in one parenthesis multiplies everything in the other parenthesis, and we get 4 terms like that. Sometimes people get confused about the square root part. So we have square root of t squared plus 9 times square root of t squared plus 9. So that's square root of t squared plus 9 squared. And that's where that first term came from. Is that okay? Just to clarify further, like x times x is x squared. So is that okay? There was some confusion about that in my last section, so I just want to make sure that's in there right. All righty. All right, so if we keep going here, you'll see lots of stuff cancels. I'm going to, yeah, I guess I'll just keep going. So one thing that cancels is the square is going to cancel out the square root. And then you have +3 square roots, -3 square roots, and so those also cancel. And then 3 times 3 will become 9, right? So we have t squared plus 9 minus 9. See if I can make this happen. Damn it. All right, it's fine. Just gonna keep going. Is that okay? Things are canceling, right? And then we have +9 minus 9. So that's nice. And then the t squareds are also going to cancel. So we have this. And so the t squareds also cancel. And so we just have something that we can now plug a 0 into. But that was the whole goal here, is we wanted to get down. We couldn't plug a 0 into it originally. Now if we plug a 0 into this thing, okay. And we didn't change anything. We just multiplied by the number 1 and did some algebra. And so that was really nice because now we can actually solve this thing by hand. This is like this, I would describe this work as the scratch work. And I'm going to write down sort of like the final answer, I would call it. Thoughts about the algebra? That's obviously the important part, I would say. Pause and folks catch up. So kind of the final answer, I think the best way to describe the final answer would be, we wanted to write down our original limit, which was this. We found that you can't plug a 0 in there. So we did some algebra and we turned out, right? So you don't have to actually rewrite all this stuff. We know that this thing turns into that. So I'm just going to say, well, it turns out that that limit is the same thing as the limit of this function we just came up with. Based on the work right above there, right? And now we can just go ahead and plug a 0 in. And so I'm going to stop writing the limit, and that'll be the answer. Let me go ahead and graph this on my computer real quick so I can remind myself what it looks like. I think it kind of looks like that one now. That's right, I forgot this part. T squared plus 9 minus 3. Yeah. So I'll just draw this one over here, but it turns out this graph, the graph of this thing, kind of like goes up, comes down, just a hole right here. That's approximately the point. So if you walk along this graph, same thing as what we came up with. If you graph either one of those things, it would look like this. The difference is this one's got the hole in it, and this one doesn't have the hole. This one fills in the hole. But we just look at the picture. We do the left-hand limit. We're walking along this towards that point. We do the right-hand limit. We're also walking along towards that point. The way we can find it by hand is by doing this. But, oh no. Questions? Which one are you talking about? So this one is approaching 0 though, right? Yeah. So where do you see 2? Oh, if the limit was approaching 2 of this one, you can plug 2 into the original function. And so you could just plug 2 right in there, and that's what would be the answer. We're looking at 2. 2 would be up here where there's not. You can plug 2 right into that. The problem is when there's a hole, there's an aspect. Not if there's a square root and plus or minus something. That's usually going to be the approach for that. I mean, it's possible like you try the conjugate on a problem that's not supposed to be the conjugate, for example. It's not going to work in those situations. But in one like this, where you have square root plus or minus something, and that's leading to an issue, it should work. Other thoughts? It's good thought. Other questions? All right, let's look at the next one. Let's think about which one of these three options that we could possibly do on this one, right? So I want to look at the one, come on, the one down here. We've got these potential options. I just said that you want to use the conjugate, which we just did if there's a square root. So there's no square root in this one. So we shouldn't do that. I'll just let you know that this one, the second one, this 1 over x to the n thing, we use that for infinite limits. And we'll look at that next time more than likely. And so it's got to be one of the other two. It's got to be either B or C. Factoring and canceling is possible here because you can factor x squared minus 1 plus 1 x minus 1, but nothing's going to cancel it. So, this is like one of those examples that, maybe you chose one thing that you thought was going to work. Maybe you thought was a factor and cancel problem. You start doing that, but it doesn't work. You might reevaluate and try one of the other. Right. And so that really just leads combined terms. And that fits here because we have two separate terms. And so heck, let's try to combine them, right? It seems like that would make sense in this situation. Right, just trying to walk through like how to choose the correct approach. Does that make sense that combining things is a good idea here? And I guess actually the first thing that we should always do, I should follow my own advice. What was the thing I suggested we do before we try any of these things? Just try to plug in the number in, right? Just try plugging the number in. That might work. So let's try just plugging the number in. If I plug in 1, right, we're trying to approach 1 here, I'll get 1 over 1 minus 1, 2 over 1 minus 1. So we get a couple things over 0. That's indeterminate. So I'm sorry, I know I wrote this right, so I know we need one of the techniques, blah, 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 but you should always be thinking, try to plug the number in. And so let me backtrack then. So let's try combining terms because that seems to make the most sense, right? So let's combine terms. Oh gosh, we've got to add fractions. That's okay. We're in calculus. We can add fractions. I know it. And I really mean, like, I'm kind of kidding here a little bit. But don't let fractions be something that prevents you from understanding this stuff. Like, I really mean that. You're in calculus. You know how to add fractions. You can. Even if you need a little review, you need some help, I will help you. But don't let fractions or something silly like that stop you from being successful. So how do we do that? Who feels a little bit confident? How do we find, we need a common denominator. Let me give you that hint. What's the first step in sort of figuring out what that is? Okay, so real quick, it sounds like you want to do this, but if you do that, you need to do this, which gives you a whole bunch of stuff. So that's a good thought, but just keep that in mind. That's an important thing to remember. There's actually, like, I'm trying to get at something specific, like there's, and maybe someone in my pre-calc class from last semester can help us. When you want to add fractions, you do something to the denominator first. Yeah, that's what we want to do, but how do we know what they are first? It's an F word. It's a nice F word. We want to factor. So x squared minus 1 factors. Right, we mentioned that a second ago. That factors into x plus 1, x minus 1. And that's helpful because they both got the x minus 1, right? So we should always factor the denominator if we want to add fractions. That's the kind of the key thing. Right? We see they both have x minus 1 already. So we just want to give it the x plus 1. I forget who was saying that, right? We want to give it the what it's missing. Can I clarify that before we keep going? That's an important thing there. Because otherwise, we're just going to get stuck on this first step, right? Don't let fractions be the thing that gets you down there. I really mean that. So the way we move forward with that, let me do some magic there real quick. So the way we move forward is by doing this, right? Because then they'll both have x plus 1, x minus 1. Okay. And so we'll have x plus 1 minus 2 over that thing. In addition to just fractions in general, if you need some help with some of these prerequisite topics like fractions or factoring or solving equations, anything from what would be considered pre-calc, let me know. I'm happy to either sit with you, or I've got lots of pre-calc notes that I can send you as a reference. Even if you were in my class last semester and you threw them out for some reason, I will resend them to you as a reference. And so when you're inside a problem, you don't feel like fractions are stopping you. Let me know. Is this okay so far? If we have the same denominator, so 1 times x plus 1 is x plus 1. Okay. And then we can do 1 minus 2, which is minus 1. So this will be x minus 1. See where this is going? And then what happens? Just took out the red ink. What's going to happen? They're going to cancel. The x minus 1s are going to cancel. Right? We've got an x minus 1 and x minus 1 in the bottom. They cancel. And now we have something we can plug a 1 into. That's sort of the final answer there is saying, hey, we want to do this original limit. Oops, that should be the number 1. We couldn't do it with that one. It was indeterminate. So on the numerator, we've got 1 minus 2, which is minus 1. Right, so once we have a common denominator, we like combine the numerator. Okay, so everyone see that? Okay. Common denominator. This came from this one, 2 from this one, so those 2 combine. So anyway, what I was saying is we want to do this original. I'm writing in blue in the bottom corner here. We want to do the original limit. We couldn't plug a 1 in there, but we did some algebra, and we know that it's actually the same thing as this function. That's something, oops, 1. That's something we can plug a 1 into. Let me draw what that picture looks like. I always, actually, I'm not sure what that one looks like. I was going to draw that. It's going to be some funky rational thing. Oh, I do know what that looks like, actually. And how do I know what it looks like? Because this is a transformation of 1 over x. So those folks in my pre-calc class again. On my pre-calc stuff. And this is a transformation of 1 over x that was moved to the right one, left one. What looks like. Wait a second, 1 over x. No, I'm confused for sure. Let me double check. What I'm thinking does not jive with the results. So let me verify. Oh, that's right. Oh, that's right. Okay. So it looks like this. under 1, there's a hole. And so what this point is at 1/2. So it's like when you walk along this thing from the right, you're approaching the same point you are as from the left, but there's a hole there, but it's at 1/2. And we were able to sort of see that from this. And so this thing I'm drawing with the hole in it is the original function. The function we ended up with, sorry, what happens when this thing turns off? The function we ended up with is this thing with the hole filled into it. Thoughts? Clarify something about that? Just remind myself how far I got in the other class. I think I just finished with this last thing in the other class, so I think I will stop after this last thing here. I had a lot of technical difficulties in my last class. I was originally trying to beam my iPad to Zoom, and it was causing all kinds of delays, and I was fiddling around with it. It was kind of a mess. Anyway, that's why we have a little more time in this class. Can I answer some questions about this stuff yet so far? We've looked at 2 techniques. We've looked at conjugate over conjugate, combining terms. Those are the 2 things we've done so far. Anything else you want to talk about at this point? I'm just going to slide down in case people are writing that. All right. Is this still recording, I hope? Yes. So the last one I'm going to look at today is this middle one. We'll look at this one next time. So this is an infinite limit. We haven't seen any infinite limits yet. So I'm going to take a second to talk about what an infinite limit is before we look at that. Just curious. Should we do that later? No. Okay. And then what do you think we do on this one? Just like curiosity. We've already seen this one, this technique. Just curious what you think. Which one does that look like, you think? It's a conjugate one, yeah, because it's got a square root plus or minus something else. So we'll use the conjugate on that one, but that'll be a good thing to review next time. So let's do this middle one though. And so going back to the options again, there's no square root, right? So it's not going to be a conjugate one. This is just for square roots. I mentioned a couple times, but we use 1 over x to the n for infinite limits. We'll look at that next time. There's nothing to combine in that one. It's just one function, so it's not a combining one. And so it's the only thing left is factoring and canceling. We're just trying to, again, think about how you know which one to use, right? So, but I also didn't follow my own advice. What should we always try first? Just try plugging the number in. So if we plug in 2, right, we're trying to approach 2, we'll get 2 squared minus 4 over 2 minus 2, which is just 0 over 0 again. So we do need a technique. Surprise, surprise, and we should try factoring. So x squared minus 4 factors into. Hope this should cancel, so like it should be one of the things in the bottom, right? So that should give you a hint, right? If we know that this is in the bottom, like I'm just trying to give you a hint about factoring. If we know something's going to end up canceling because this is a factor and cancel problem, that should probably be one of the things that factors in. We want it to cancel. So the other thing that factors into is x plus 2. And it cancels, like we just said. Right? Minus 2's cancel, and we're just going to get x plus 2. Let me do this one with the limit the whole time, actually. This is a good opportunity to do this another way. So I'm going to write the limit the whole time. All right, I just wrote the limit in there. We factored and canceled. I'm going to write the limit again because we haven't taken the limit yet. And now I'm going to plug the number in, so I'm not going to write limit anymore. I always think these ones are kind of interesting because it's like Well, first of all, are there questions about the factoring or the canceling? This to me is a pretty interesting thing because we started out with this function that's a fraction and it has a square in the numerator, and somehow that's the exact same thing as this straight line. That's surprising to me whenever I think about it. So if we were going to graph this, actually I have to bring the graph here, so I'll draw the picture here. If we graph this thing, it looks like the line x plus 2, but it has a hole in it. So x plus 2 has a y-intercept of 2 and a slope of 1. So it looks just like that graph there, except at the point 2, there's a hole. So it's a straight line with a hole in it. That's how you end up with holes, is when you have some fraction thing and it cancels out a factor. But just looking at the picture, right, the right-hand limit both exists and they both approach 4. Okay. I'm gonna stop there. Can I answer questions about math before I say one other thing just in general? All right. So the first math homework, which is on this limit stuff, is due next Wednesday. We're almost at the end of it. By the end of the next class, you'll be fully prepared. You can do 90+% of it by now. So don't wait on it, is what I'm trying to say. Please remember that the first quiz is due tonight, and it's this super easy quiz that's just getting you to fill out the syllabus. It's more like a, hey, can you follow basic instructions thing more than an assessment. So don't blow it. I really mean that. I get kind of annoyed when I'm trying to give you points and you just kind of throw them away. I don't get annoyed. I don't really care that much, but I'd like to give you points is what I'm trying to say. So don't make me track you down and force you to get the points. Take a copy of it if you want on the way out. Otherwise, it's on Blackboard. Let me know if you need some help with that. Question? I'm sorry? We have, I think, 3 tests and a final, if I remember that correctly. Yes, yeah. And we'll do all tests and quizzes are going to be in this room. Yeah. And I mean, on Fridays. Other thoughts about anything? Yeah. I think I wrote that down. It's either 2 or 3. Oh yeah, that's okay. Sometimes people count the final as a test, which it technically is. That's okay. Other thoughts? All right. Thank you guys very much. I'm going to stop recording this. I'm going to post this session just like I post every other session. So if you want to take a look at this,